When a Shahed 139 drone entered the airspace near the USS Abraham Lincoln in the Arabian Sea, it didn't encounter a ship, it encountered a network. The F-35C that intercepted it never needed to see the drone first. The kill web already had it. What happened next wasn't a dogfight, it was a logistics problem being solved in real time. The Arabian Sea is not an incidental operating area. It sits at the intersection of three strategic corridors: the Persian Gulf to the northwest, the Indian Ocean to the south, and the Gulf of Oman, providing the critical transit lane that connects Iranian territorial waters to open ocean. When a carrier strike group operates in that space, it is not simply present. It is making a geometric argument about access, reach, and the cost of challenging either. The USS Abraham Lincoln has operated in that corridor multiple times across different deployment cycles. The specific intercept in question involved a Shahed 139, Iran's domestically designated variant of what the broader intelligence community tracks as a one-way attack drone, adapted from the Shahed 136 series and modified for longer-range reconnaissance and strike profiles. The Shahed 139 is not a sophisticated platform in the Western sensor fusion sense. It is a simple, slow, propeller-driven airframe with a modest radar cross-section and a low thermal signature at cruise altitude. Its value is not in individual capability, it is in volume, unit cost, and the operational friction it creates for defenders who must decide how to respond to it. The detection sequence for an approach like this does not begin with the ship. That is the first thing most assessments get wrong. By the time any shipboard system is processing a track on an inbound drone, that drone has already been characterized by multiple nodes in the network, operating well outside the strike group's visual or close-range sensor envelope. The E-2D Advanced Hawkeye is where that chain typically begins in a carrier air wing context. The E-2D is a turboprop airborne early warning aircraft, and its AN/APY-9 radar system is capable of tracking small, slow-moving airborne contacts at extended ranges, including targets that would be masked by sea clutter or terrain at lower altitudes. It operates in a persistent orbit pattern, and its data feeds directly into the network rather than requiring voice relay to a command station. What the E-2D sees, the network knows. That network has a formal designation, the Naval Integrated Fire Control Counter-Air System, or NIFCCA. It is not a weapon, it is a coordination architecture. NIFCCA allows sensors on one platform, an aircraft, a ship, or a drone, to cue weapons on a completely different platform, without requiring that second platform to independently detect or track the target. In practice, this means an F-35C can receive targeting data from the E-2D, execute an intercept, and never once activate its own radar in a way that would alert the target. The F-35C becomes an effector in a network, rather than an independent hunter. The drone it is intercepting may never know it has been tracked. The F-35C's own sensor suite compounds this. Its AN/APG-81 radar, its distributed aperture system, providing 360-degree infrared awareness, and its electronic support measures package all contribute data to what the platform calls sensor fusion, a continuous, automatically integrated picture of the battle space drawn from every available sensor simultaneously. A pilot in an F-35C is not interpreting individual data streams. They are looking at a synthesized tactical display built from radar, infrared, passive electronic intelligence, and data-linked external feeds, all merged into a single coherent picture. Against a Shahed 139, operating on a simple autopilot, that sensor architecture is not challenged. The engagement is a geometry problem, and the geometry was solved before the intercept aircraft was even airborne. The Aegis destroyers in the strike group add another layer to this architecture. Each Aegis-equipped ship runs the Cooperative Engagement Capability, or CEC, which allows sensor data and fire control solutions to be shared laterally across the formation. A destroyer on the outer ring of the strike group that acquires a contact can pass a fire control quality track to a cruiser or to another destroyer, allowing a weapon to be fired from one hull using targeting data generated by another. This is not a new concept, but the fidelity and speed at which it now operates has changed the effective engagement geometry of the entire formation. The strike group does not defend from its center, it defends from its edges. using a shared picture that no single platform generates alone. Now consider the Shahed 139 in this context, from a resource standpoint, because this is where the analysis becomes clarifying. An individual Shahed 139 is estimated to cost between $20,000 and $50,000, depending on component sourcing, a figure that varies based on whether sanctioned materials were successfully substituted and which manufacturing batch is being assessed. A standard AIM-9X Sidewinder missile, which is a likely intercept option in this engagement profile, costs approximately $400,000 per round. A carrier strike group represents a deployed capital investment in the range of $15 to $20 billion across hulls, aircraft, and ordnance. The math of the Shahed 139 as a weapon system is not about the individual drone defeating the carrier. It is about forcing the defender to expend expensive, finite magazine inventory against cheap, replaceable airframes. This is the core industrial logic of the platform. Iran's drone manufacturing capacity is meaningful. The Shahed series has been produced in sufficient volume to supply proxy forces in Yemen, Iraq, and Syria, and has been transferred to Russia for operational use in Ukraine at scale. The production infrastructure is dispersed and relatively low cost. Iran is not dependent on precision semiconductor supply chains in the same way Western guided munitions programs are. The drone can be assembled with commercially available components and relatively basic manufacturing tolerances, because it does not need to be precise, it needs to be numerous. For the carrier strike group, the relevant constraint is not detection or intercept capability. It is magazine depth and sortie generation rate. A carrier air wing can sustain a defined number of sorties per day, and each sortie has a defined loadout. Intercepting one Shahed 139 consumes a missile. Intercepting 40 in a compressed time frame requires both the inventory and the sustained sortie tempo to support it. The question saturation scenarios are actually asking is not whether the carrier can defend itself against a single contact. It is whether the industrial and logistical depth behind the strike group can sustain defensive operations against a campaign designed to drain it. That is a question about supply chains, not sensors. To make that concrete, consider what a credible saturation attempt would actually require. A Shahed 139 cruises at roughly 185 kilometers per hour. Its operational range is estimated at around 2,000 kilometers, depending on payload and routing. To generate meaningful intercept pressure on a carrier strike group operating in the Central Arabian Sea, an adversary would need to launch from positions capable of sustaining that range, either from Iranian mainland sites, forward proxy positions in Yemen, or maritime platforms operating closer to the threat axis. The geometry matters because it determines how compressed the intercept timeline becomes and how many drones arrive in a single engagement window rather than sequentially. A sequential trickle of drones is a manageable intercept problem. The network handles it the same way it handled the single contact: detection, track, handoff, intercept. The scenario that stresses the defensive architecture is simultaneous arrival from multiple vectors, ideally with enough density that the fire control system must prioritize rather than simply queue. Analysts who model this estimate that generating genuine saturation pressure against a carrier strike group's layered defense would require dozens to potentially over 100 simultaneous inbound contacts across multiple approach corridors. That is not a single launch event. It is a coordinated, sustained campaign requiring pre-positioned assets, synchronized timing, and a manufacturing base capable of absorbing the expenditure and reloading for follow-on waves. Iran's current assessed production rate for the Shahed series, across all variants, is estimated in the range of several hundred to perhaps 2,000 units annually, a figure that has grown since 2022, but remains constrained by component availability under sanctions pressure. Russia's consumption of Shahed drones in Ukraine has run into the hundreds per month during peak operational periods, which means the shared production base is already under significant demand. The units available for Arabian Sea contingency operations are not unlimited, and the logistics of forward positioning sufficient stockpiles to execute a genuine saturation campaign would require infrastructure signatures that U.S. intelligence collection is specifically designed to detect. The threat is real as a concept. As a near-term executable operational plan, it faces significant industrial and logistical constraints. The sustainment side of the carrier's equation deserves equal precision. A Nimitz or Gerald R. Ford-class carrier, in a deployed configuration, carries a significant loadout of air-to-air and strike weapons. But that inventory is not replenished from thin air. The supply chain runs from U.S. defense manufacturers, Raytheon for the AIM-9X, for example, through naval weapons stations, to fast combat support ships and ammunition ships conducting underway replenishment, or UNREP, operations. A standard UNREP evolution can transfer thousands of tons of fuel, food, and ordnance in a single connected period, but it requires the support ship to be present, loaded, and operating within range. The strike group's sustained defensive capacity is therefore a function not just of what it carries, but of how quickly the logistics tail behind it can regenerate that inventory. That logistics tail runs back to American industrial capacity, and American industrial capacity for guided munitions, while significant, has its own production rate ceilings that the defense industrial base has been working to expand since 2022. This is also why the Arabian Sea operating area is strategically significant beyond any single engagement. A carrier in that position simultaneously covers the Gulf approaches, maintains response options for contingencies in the Indian Ocean, and provides a persistent signal to regional actors about the cost of escalation. The drone intercept is, in that sense, a data point in a longer deterrence calculation. Iran's strategic interest in probing carrier defense is not necessarily to destroy a ship. It is to gather information about detection thresholds, intercept protocols, and response timing, data that informs future planning regardless of the immediate outcome. Whether drone swarms meaningfully change this equation is a question the defense community continues to assess with genuine analytical disagreement. The argument for swarms rests on magazine exhaustion and coordination overhead. The argument against rests on the same network architecture described here, a system specifically designed to manage simultaneous distributed threats through shared fire control rather than individual intercept decisions. The honest answer is that saturation at sufficient scale would stress any defensive system. The relevant variable is whether the industrial capacity to generate that scale of simultaneous attack exists, can be sustained, and can survive the detection and interdiction efforts that would begin well before the first drone crosses the launch threshold. On all three counts, the current assessed answer is no, but that assessment carries a shelf life, and both sides of this equation are actively investing to change it. The invisible wall around a carrier strike group is not a ship, and it is not a missile. It is a coordination system underwritten by industrial depth, the software-defined architecture of NIFCCA, the sensor fusion of the F-35C, the cooperative engagement grid of the Aegis formation, and behind all of it, the manufacturing base, the supply depots, the replenishment vessels, and the production lines that keep every layer of that system loaded and functional. The wall exists before the drone launches. It is built into the detection range of the E-2D, the passive sensor aperture of the F-35C, and the intelligence collection architecture that monitors launch sites and production facilities before a single airframe takes off. The Shahed 139 didn't vanish because it encountered something it couldn't defeat. It vanished because the system it flew into had already accounted for it. That is what the business of modern naval defense actually looks like. Not a single intercept, but a chain of decisions, logistics, and industrial commitments that began long before the engagement clock started.